Welcome everyone to the week 12 tutorial session of Galois theory MA70. Today we'll discuss some sample questions related to week 12 lectures. Let's begin. Let okay. Let L over K be a finite separable extension that is not normal, and let N be a normal closure of L over K. Show that Galois group of L over K is non-abelian. Okay, so let's see what can we do here. L over K is given to be a finite separable extension. And we also know that this is not a normal extension. And okay, there is some correction in this. This is N. So N is given to be a normal closure of L over K, and we need to show that Galois group of N over K is non-abelian. Okay, so okay, let's browse through some known notions. So we already know that, okay, even you were asking earlier, maybe we can see this theorem, fundamental theorem of Galois theory. What does this say? If the extension, so I'm just saying E over K because I don't want to be confused with the given notions. So this is Galois. This is given to be Galois, and so the subgroups are okay. So what is the correspondence say? You consider Galois group of E over K. So it is Galois means Galois group of E over K is same as the cardinality of this set is same as the cardinality vector space dimension of E over K, right? That is always less than or equal to, but in when it becomes equal, then the extension is said to be the Galois extension. So Galois over K, you consider one side there is this group, and on the other hand you consider the extension. So okay, E over K, or maybe if you want, maybe just E, or okay. One side is field, and the other side is the Galois group of corresponding to it. So from this correspondence, so if you consider any subgroup, let's say H subgroup of E over K, H is a subgroup of this Galois group, or maybe I can just write G. You consider H subgroup of G, okay, this subgroup notation. How this maps to a subfield? You just take the fixed field of E and fixed field of E and corresponding to H. So what does this mean? All those element of alpha belongs to E such that sigma of alpha is same as alpha, where sigma belongs to H. H is a automorphism. So Galois group is what? Galois group is the automorphism. Automorphism group of E, which fix K algebra automorphisms of E, right? So sigma is also automorphism because this is just H is a subgroup of G. So this is the fixed field. So this is for all sigma. So all those elements of E such that sigma of alpha is same as alpha for all alpha, sigma belongs to H, right? And from the other side, what do we have? You consider a subfield. So this is a subfield, and you will get, what will you get? What will you get as a subgroup? So well, there is this. So you have this extension, Now you have something m in between. So even in the statement of fundamental theorem itself, or you can even prove that this is also Galois. If this is a Galois extension, then this is also Galois, because now you know, for example, you know that the Galois extensions are basically normal and separable extension. This is if and only if condition. So if k to e is Galois, that means it is a normal extension, all the roots are there. Like if there is one root, then all the roots are there. Or you can even say that this is a splitting field, or splitting field of a bunch of polynomials, because we are talking about finite extensions for us right now. Okay. Yeah, so I should say this is a finite Galois extension. Okay. And the other thing is, all the polynomials are separable. For every element you consider the minimal polynomial, and that will be separable. So if this happens for e over k, then it will happen for e over m, but it need not be true that this will be a Galois extension, right? So here this maps to Galois group of e over m. So that is the correspondence we have. Is that clear? So I'm just recalling whatever we have done in the lectures. Is that clear?
Yes, yes, ma'am.
Okay. Now, very good. So now what happens if m over k? Now what is the relation with when can you say that m over k is also Galois? There comes this Galois correspondence. And Galois correspondence says m over k will also be Galois, is Galois, if and only uh, if this is a normal subgroup. The fixed field of sorry, this is also already a field. If and all, so yeah, this extension is Galois if how shall, yeah, so m over k, this is a normal subgroup of G. So G is basically this Galois group of E over K. Okay, I'm just relating using the same notations. So that's when it becomes so smooth, like the when for example the Galois extension, for example, let's say the Galois group of E over K is abelian, let's say, then what will happen from the Galois correspondence? This Galois group, so this is G, so all the subgroups will be what? Subgroups of G will be normal, right?
Yes, yes, all
Right.
normal.
So this will be normal. So the all the intermediate extensions will be Galois.
Okay.
Okay. So so these are all the information we have. Now let's see. Actually, we have done this question now, but let's see. Uh, what do we need now? L over K is a finite separable extension. So what can you say about that? So
It is a simple extension.
exactly, very good. So L over K is simple.
There is exist primitive element.
Yeah, there will exist a primitive element. Very good. So I'll just, okay, I'll take another page. So what do we have? Proof, solution of the question maybe. Or anyway, so L over yeah, it was L only. L over K is finite separable. This implies, by primitive element theorem, L over K is simple. That means, that is, there exists some element, let's say x, in L such that L is equal to kx, right? Okay, now what is n? N is given to be a normal closure, of L over K. So what does that mean? Firstly, this is just a finite separable extension. So you cannot say that this is a Galois extension, because uh, this this has been already proved in the class that Galois extension means this is a normal extension plus this is a separable extension. L over K is separable. So there are two conditions required: separability and normal. Again, I am talking about finite extensions for now. Okay. So normal and normal. So separable, it is given already. So what are the requirements for these two things? Separable means every irreducible polynomial should not have a repeated root, right? Multiple roots should not be there. And for normal extension, what should be the thing? You consider any element of x. So what is the requirement? You take, or maybe we don't want to be confused by the notation. So you consider y belongs to L, then you consider mu y comma k, right? Because that will be the minimal polynomial of y over k, and so this is in kx. Now what do you need? You just so normal implies mu y comma k splits into linear factors. Why is that so? Because y is there, so one root is there. Normal extension says if there is any one root of any irreducible polynomial, then all the roots will be there. That is the basic definition of normal extension. So you start with an element itself and you consider the minimal polynomial. So you already know y belongs to the uh, roots of mu yk. Now, if I'm talking about roots, I can say some algebraic closure or splitting field, right? Some splitting field of mu. Okay, so y is already there, and y also belongs to L. So this is in the intersection. So one root is there in L. So all the roots will be there in L if it is a normal extension. But it is not given that this is a normal extension. But one can make it a normal extension, and this is already separable, so there is no problem. So what we want to say, so what is the meaning of so I again used L. I'll just use F for, so that there will be no confusion. Yeah. So this is some definition. So what is n? N means, so you firstly you have, by the primitive element theorem, L is equal to kx, right? Now so this is separable but not normal. This is already given even, but not normal. It could be normal or not, but it is given to be that this is not a normal extension. So definitely this is not going to be a Galois extension. This implies not Galois. Okay. Now okay, let's see what are the things we have. So L is equal to kx. So you consider n, which will be what? K, and you attach all the zeros of x in k. Sorry, not in k. So zeros of mu x comma k. Okay, and where will that be? In some algebraic closure, okay, of mu, or maybe splitting field, whatever you want to call it, that exists. We already know that splitting field of mu exists, so you can also think there. Okay, so n is basically what? N is basically splitting field of mu xk, because what we are doing, we are making it a normal closure. So normal closure means you just attach all the roots because x is already there. So to make it a normal extension, uh, you have to give all the roots of that minimal polynomial, right? That should split, and we have already proved that. So kx kx1 to xn will be a normal extension if and only if this maybe L is the splitting field of sorry splitting field of um, product mu xi comma k. So that we have also proved in one of the tutorials, right? So basically normal extensions are mostly the splitting fields of some polynomials. Is that okay? So n is just the splitting field of mu x comma k. That is by definition what do we call a normal closure of L over k. Is that okay? Any doubt?
Okay.
Okay.
Okay. I one second just.
Mhm. So what you are doing, you consider L is equal to kx. You consider as so that is given to be a separable extension, which is not normal. It is given. So what you are doing, so that is there is only one element attached to k, so that it becomes a new field, right? So you consider the minimal polynomial of that, and and you know that normal extensions are just the splitting field of all these elements itself, x1 to xn. So you just take all the roots of mu xk means minimal polynomial of x in k. That's we always do. So you just
Ma'am, notation n is equal to k. The algebraic closure.
uh, so
Okay.
so roots will be somewhere, right? So we write, I just write e.
The mu x k, it is the zero set of.
Yeah, this is the zero set. This same notation I'm using, which
Okay.
yeah. So yeah, v of some polynomial f in e are the zeros of f in e. That is the definition. So what we are saying here, E is the algebraic closure of, or if you want, you can just take a splitting field itself, because it doesn't matter what we need. We just need all the roots should lie there. Like we don't want to leave any of the roots. So splitting field of mu xk. You can take like you can write like this. Doesn't matter. It's just you attach all the roots of mu xk. So even one can say that n is actually the splitting field of mu xk. Just if and only if things, because we are what we are doing k, and you have all the roots. So that is the splitting field of mu xk. So that is all happening by definitions. So this is said to be the normal closure, right, of L over K, because we have extended L. So what we did, we had this, and this was a separable extension, and we have extended it. So all is happening in finiteness. So this is also finite because roots will be finite. So this cannot be a infinite extension, this normal extension. So this is normal closure of L over K. Now what you can observe, this is normal. Second thing, this will be separable also, because L is separable, N has to be separable. Why? So we are talking about N over K. This is a normal extension because this is the normal closure itself. So now what we are saying, this will be separable also, because L over K is separable. And what does separability mean? Separability mean you take any f in kx, okay, So, or maybe you can just take elements and take the minimal polynomial, and that should be, polynomial should be separable. So f should be separable. If f is separable in L, it does not have multiple root, then how can it have multiple roots in M? Because that is just some extension itself. F is in Kx only, right? So it cannot have right. It cannot have one second. Will it be in Lx or Kx?
Yes.
uh, this f. So L over K is a separable extension. What does this mean?
Yes. Every irreducible polynomial has simple root.
Every irreducible. So
Polynomial
you,
from kx.
right. So yeah, you take any x, you take mu xk even. That is one definition which I am using. So you take that, and mu xk is separable. You can think like this also. So it doesn't matter.
Normal
Uh,
closure are
or
algebraic.
maybe not. Sorry.
Algebraic closure and normal closure are
Oh, so algebraic closure means what? Algebraic closure means you are saying
uh, uh,
roots are
uh,
there, all the roots are
uh,
there.
roots are there, and it is the maximal extension, algebraic extension of
Mm-hmm.
this base field. Okay.
Yeah. So normal extension does not require a root should be there, right? But algebraic closure require. So sorry. Normal implies what? Normal implies if there is a root. So I should say n over k. X belongs to n, and so if there is a root, if there exists a root, uh, x or maybe y, there is a root of f in n, then all the roots will be there.
Hmm.
All the roots, of course, reducible polynomial f, then all the roots of f will be there, right? So
Right.
all the roots will be in n. So that is about normality, okay? And algebraic closure means, so what you are doing in normal closure, you have just uh, made it that every polynomial will split. Not every, if there is a root of that polynomial in the field, then the polynomial will split. But algebraic closure says all the polynomials should split, all the irreducible polynomials, or even you can just say polynomials, all the polynomials in Kx splits into linear factors. It does not require one root should be there. I can give an example. So, for example, you take q root 2, okay, and you take this. So, you know that root 2 is a root. Okay, so should I take in between? But doesn't matter. So q root 2 is a normal closure, because if there is a root, then all the roots one second, yeah, if there is a root, then all the roots will be there. For example, you take x square minus 2, right? Then root 2 is there and minus root 2 is there. But when you take okay, capital X, because this I'm using for a polynomial, but this does not split here, right? X square minus 2 3 does not split in q root 2, right? Because root 3 is not there. So q root 2 is, this implies q root 2 is not a uh, yeah, is not an algebraic closure. It's not an algebraic closure of q, right? But this is actually a normal closure of q. Actually, there is one more thing I should not say like this. I just want to distinguish, okay? So one thing is it says all the polynomials should split. On the other hand, it says that uh, so yeah. I should not say closure because there is x square minus 2. Okay, let me do like this maybe. Mm, yeah, you just take this. For example, you take q, uh, because q is itself. No, mind. Okay, you take this. I'm just modifying my example. So you take q, cube root of 2, and you take eta, and this is you take cube root of 2. You know that x cube minus 2, I'm talking about this polynomial, right? So there is a root here, but not all the roots are here because zeta is not there, right?
Yes.
Okay. So uh, this this extension, so in our case you can think of again, I'll not compare with that because that is not a primitive thing, but you know that this extension is not normal because the roots of x cube minus 3 minus 2 are not there. All the roots are not there. One root is there, but not all the roots, right? So this is not a normal extension, right?
Yes.
But now you make it a normal extension. So this extension you attached zeta, and this become a normal extension. Even you can see, you can actually check that because this is why this is a normal extension, even closure also. Why this is true? Because you have also seen that this is a splitting field of the minimal polynomials of this, right? So that is also that. So this is a normal extension, and roots of x cube minus 2 are there, but this is not a algebraic closure because not an algebraic closure, or if you want, not an algebraic closure of q cube root of 2. Why? Because this is not algebraically closed, because if you consider this polynomial, let's say, then roots are not there. Roots of this belongs to here, right? This belongs to q cube root of 2. Roots of this, which is there, is not in, or not in. Okay, do you understand the difference? So it's like because x cube minus 3 does not have any root here, okay? It does not have,
Is
yeah.
q minus 3, this belongs to the cube root of 2 x. I mean,
Because I'm
where
take
element, yeah,
because it is in
element of,
qx. I'm just writing because I
yes,
want,
yes, yeah,
yeah.
q is the subfield of that qx. Okay.
Yeah. So
Uh,
this is a subfield, so even I can
okay,
write.
then it belongs to that. Okay,
Yeah.
okay.
I just
Yes, yes.
wanted to keep it in the base
Ah,
field because
yes,
base field
yes.
I am taking that.
Okay, okay.
So this is some extension. Now
Mm-hmm. Okay.
this extension is, even you can start with q. I just wanted to say that this is from here. This is a
Yes.
normal closure, but this is not an algebraic closure because
This term also we knew normal closure. Today it is also I am just going to associate in this class normal closure. Algebraic closure is known to us.
yeah, I know because sometimes this, okay, if for example in this situation it is given that this is a separable extension, so if you just take normal extension it will become a Galois extension because extension of a separable extension will be separable because, as I said, the polynomial will not have multiple root. If that is not true for L over K, why how will it be true for N over K? One explanation is basically, if you take any irreducible polynomial in L over K, then uh, the irreducible polynomial in n over k will be some divide. So minimal polynomial of any x. So I can take y because x I have already chosen for something. So you take this in L, and you take y in n. So n is a bigger extension. Okay. So okay, this will divide I should write other way. This should divide, right? Because the polynomial will further split, or might not be, doesn't matter, but it will divide, right? We have done that earlier also. So because that is just extension ky and everything. So basically, so you have, so if you remember that this extension and this extension, you just take that, and uh, this has to divide, because in the modulo, in that epsilon, not epsilon, what do we say, evaluation map. So in the evaluation map, kernel will be kernel of uh, the small kernel of this one, right? Kernel of this one will contain this polynomial, so it has to divide. So that's why. Okay, so this will divide, and if this is separate, so if this is separable, then its divisors are also separable, because separability means there is no multiple root. So how will it have multiple root in the divisors also, if that is not there in the main polynomial, right? So this will be a separable extension. So sometimes if a normal closure you have considered for a separable extension, it is also said to be so normal closure, it is also said to be the Galois closure. So that is also a terminology sometimes people use, Galois closure. So you're just making it Galois. But if it is not separable, then there is some work you need to do to make it a Galois, like you consider some Galois closure. So because you have to remove things, because if there are some polynomials which are not separable, then how will you extend it? So it's like an integral domain thing. So if it is an integral domain, then you can make it a field by inverting it. But it is if it is not an integral domain, then you have to remove things like that. Okay, so what do we have now? So n over k is a Galois extension. Do you agree now? Do you agree? So
Yes,
because
it is separable and it is also normal
yeah,
closure.
yeah, these two conditions are enough. That has been proved in the class, in this week lectures. So if it is normal and separable, then this is a if and only if condition to say that this is a Galois extension. So there are three forms we know now. One is the actual definition, which just say Galois group of, let's say, n over k is equal to n over k, right? The other thing is fixed field of n of this Galois group. Okay, so if I just call it G, that will be easy for me. So fixed field of G, and this is exactly K. That is other definition. These are equivalent things, and this is normal plus separable. N over K is normal and separable. Okay, so that has been proved. Okay, so this is a Galois extension. The following are equivalent. This is a Galois extension now. So what was the question? Question was saying that if L over K be a finite separable extension that is not normal, and n is a Galois closure of L over K, then show that Galois group of n over K is non-abelian. So okay. So this is a Galois extension. Now assume the contrary. That is let L over that is Galois group of N over K is abelian. Let's say this is abelian. Then what can you say? This is abelian. Then what will happen? So you have this extension K and you have L in between. What can you say about that? About Galois group of L over K. Actually, I explained. From the Galois correspondence, what do you know?
Yes, ma'am. Galois X L over K. Okay.
Hmm.
Yes. What is the question?
So I'm saying what can you say about Galois group of L over K? So
Uh,
N over K is given to be abelian.
L over K. Okay.
Hmm.
Uh, L over.
So what do you know from the Galois fundamental theorem of Galois theory? That you have a correspondence between Galois group of N over K, and the other side you have N, like the subfields, and you have the subgroups. So you have this correspondence, and that correspondence, as I said earlier, you take any, for example, you take L here, okay, and the other side you will be taking okay, yeah, N over L. I'm not using fundamental theorem of Galois theory. I will just use Galois correspondence, and that will be enough. But anyway, so you have this, and if you take any H subgroup, this is this, and if you take any subgroup, then you know that where will you map it? You will just map it to fixed field of H n. So this is from the fundamental theorem of Galois theory. So this is that. But now this does not say anything about. This is enough when you have n over k Galois, and this is a finite Galois. Okay. And from Galois correspondence, what do you know? As I said, from the fundamental theorem of Galois theory, you know that two things. You know that this is there, and Galois group of N over L is Galois. Sorry, not. And N over L is Galois. So what does this say? If this is Galois, then this is Galois. That you know from the fundamental theorem of Galois theory. But what can you say about this extension? And Galois correspondence say L over K is Galois if and only if Galois group of L over K is normal in Galois group of N over K. So these are two things we have, the main like fundamental things to consider in Galois theory. So this will be a Galois extension only when this Galois group of L over K is normal in normal subgroup of Galois group of N over K. So Galois normal subgroup of Galois group of N over K. So now tell me, what can you say about this Galois group of L over K? You know that Galois group of N over K is abelian. So this is given to be,
Must be normal.
sorry.
This must be normal.
Yeah, exactly. That's very good. So Galois group of L over K is normal because this is abelian. Like every subgroup will be abelian, and that will be a, you know that every subgroup is normal, right? So this is normal, and if it is a normal extension, then you are done actually, because this is what the contradiction you have. So assume the contrary, that is this is abelian. So Galois group of is normal. Right. So So Galois group of L over K. Okay, what is this? These are just all those sigma uh, restricted to L and has the image in only in L. Okay, all the automorphisms. So automorphisms of N, so the automorphisms of L. Okay, this is K algebra automorphisms. So this is normal subgroup of Galois group of N over K. But then L over K will be a Galois extension. Will be a Galois extension by Galois correspondence. Because if it is normal, then the extension will be Galois, but L over K is given to be or maybe more. This implies L over K is normal, because if it is Galois, then it will be separable and normal, which is a contradiction. Right? Thus N over K, this Galois group, is not abelian. It's non-abelian.
Yes, ma'am.
Yeah.
Part, I have understood, but part wise I have understood what is in a word why contradiction, because it was given that it is no we have to, so it is non-abelian. Okay.
What we did, we assume that Galois group of N over K is abelian. Okay. So
Yes, yes.
we have to prove that Galois group of N over K is non-abelian. So assume the contrary. We
That's not,
assume
okay.
right. And when we assume Galois group of N over K is abelian, then what happened? Then Galois group of L over K will be, which is a subgroup of Galois group of N over K, but now it become normal because the Galois group is
Okay,
abelian.
yes, yes.
Okay, so every subgroup will be normal, and
Okay.
since this is already a subgroup and it became normal, from the Galois correspondence, this extension L over K will be Galois, and L over K will be Galois means L over K is normal, but it is clearly given that this is not a normal
Yep.
extension, and that's a contradiction. Thus,
Okay, okay.
for what this is this is giving a contradiction, so which is a contradiction. Which is a contradiction. Okay, and what we assumed wrong, maybe that this Galois group of N over K is abelian. So we have to say that this is non-abelian. It's not an option.
Okay. Thank
Okay,
you.
great. Okay, very good. So let's see next. Okay. So fx is in kx. This is a polynomial of degree n. Polynomial of degree n, of course, over a field K, whose Galois group is the symmetric group. So, okay, Galois group of F over K. This is by definition is the Galois group of the splitting field of F. So, one may write like this: K, and you attach all the roots of F. So, as I said, zeros of V, and okay, I should say, okay, by definition, this is a Galois group of K, and K with zeros of f in E, where E, not just f, I have to say that this is a reduced polynomial. So reduced, I'll explain what I mean. This is from the notes itself, I'm not using new notations. So this, where, okay, Galois group of this over K, where E, E is the splitting field of f, and reduced f means, so if you write, and if f is like, you can write it in this form, maybe nu 1. So you take the prime factors and you write like this, where mu belongs to K and pi i's are prime factors of f, or maybe I'll say distinct, and nu i's belongs to some, okay, ni, okay, maybe even just the positive ones. Oh, I have written, so nu i's are positive integers. Okay, so this is this. Then f is actually, you can just consider, so not f, then f, then reduced f by definition is pi 1 to pi r. So then what will happen, zeros of f will be same as zeros of reduced f, because what you are doing, you're just eliminating the powers, so that basically okay, one more thing I have to consider. So you take f to be without any power of the prime factor, and you just write like this, and you also consider E be separable. E is separable, or maybe you just say f is a separable one. Okay, doesn't matter. E is a separable extension. Okay, separable. That does not make sense much, but I just want to write like this is a you take separable one only, like separable one, I mean you assume that E is a separable extension. Okay, E is a separable extension means f is not of the kind like it is not a separable polynomial, so you assume that to be a separable one. Okay, so so when you are talking about Galois group of such thing, okay, so what we are taking saying about Galois group of f is given to be Sn.
Ma'am,
Yeah, yeah.
one point is Galois, in notation Galois k over sorry f over k. Here f is a single polynomial. In the usual notation, we must we are accustomed to write that it must be capital F. Yes.
Oh, so no. This is
There
not a.
was a confusion in the previous day assignment also. I cannot
No.
understand.
This is by definition, as I explained. That's why I explained what is Galois group of f over k. So Galois group of a polynomial. We don't talk about Galois group of a polynomial, which is not something we already know. Galois group of L over K, some extension we know that, which is just the automorphisms. But now, what is Galois group of F over K? This is like we are just writing it to make our life simple. It's just this is the Galois group of splitting field of f, like you consider that kind of. So splitting field of f over k, you consider kind of that. Okay.
Okay.
Yeah, it's just by the notation. So
Oh,
these two
okay.
dots represents we are defining something.
Okay. Okay.
Yeah. So this is by definition. Okay. Very good. So whose Galois group is the symmetric group Sn? Yeah, this be a polynomial of degree n over a field k. Right. Yeah. Now to show any splitting field of fx over k cannot be generated by fewer than n minus 1 of zeros of f. So what it is saying, you consider any splitting field. So yeah, as we said, any splitting field. So you just think about splitting field of f means what? You just take all the roots of mu, not mu, all the roots of f in some suitable splitting field. Okay.
Please scroll down slightly.
Yeah.
Yes. 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 Okay.
So you take a splitting field, let's say E. I usually denote by E, so let's keep that. So you consider this extension. So this is the splitting field. So let E be the splitting field of. So those are all isomorphic. So I'm just writing splitting field of F over K. Okay, you take that. Now, what has been asked? Show that any splitting field of fx over k, you take any splitting field, this cannot be generated by fewer than n minus 1 of zeros of f. So, and given condition is this, Galois group of f over k is Sn. So, the full subgroup. So, okay. So, let us recall some more things. Galois group of f over k, we are talking about that. So what actually Galois group do? Galois group is basically automorphisms of some splitting field. Uh, for example, a splitting field of f. Let's denote like this. I think in next question it is this notation also. But okay. So this is so I'm just writing just to denote that this is a splitting field of f. Of course, over k should be mentioned. That is we have. Okay. So automorphisms of EF over K, what will it be? And what is EF? EF is basically you attach all the zeros, right? All the where zeros of F is this set in some suitable extension. So you take algebraic closure. This polynomial will split. That's what we need. Okay, so that exists, we can use it. So so you take all the roots and that is exactly your splitting field, you know that always. So automorphism of okay, I'm messing with the notations. So this is Galois group and this is basically automorphisms of EF over K. Okay, so this is the Galois group. And what will it be? You consider all the automorphisms, take over K and you have this. Right. Now, what is happening? So, and what is n? N is already the degree of, where n is the degree of f. Okay. N is always, n is here, is the degree of f. Now, you on one hand you have k, on the other hand you have this. Okay, and what are the automorphisms? Can you tell me what will be the automorphism? So, if I consider any sigma from here, you take any sigma here, then what sigma is doing? So you know that k is already fixed. So if you just know what it is doing, so this is k algebra automorphisms. Not writing, but you know that. K-algebra automorphisms means these are already vector space automorphism, that is K-linear maps, and these are ring homomorphism, field homomorphisms, even isomorphisms. So sigma belongs to this ort of k x1 to xn. What does this mean? If you just know what it is doing on x-axis, then that is enough, right?
Yes, because K is fixed.
Yeah, k is fixed, and you know that all the if you know just on x-axis, then you know that you can multiply, and you can multiply, you can divide, and you can add, you can subtract just by these will be just k algebra thing.
Hmm.
Okay, so no issues if you just know what it where it is mapping on x-axis, then we are done. And where will it map? So sigma of xi will be what? Some xj. Why?
Yes, ma'am.
I'm
Yes.
saying, why is
Sigma
this
xi,
true?
huh?
Hmm. Why is
Sigma
this true?
sigma xi. It is permutes the roots.
Exactly, very good. So, f is a. Oh, okay, okay. One more thing. Yeah, it is fine. Uh, Not all. I'm not saying all, but for some j. Okay. What does this mean? Roots of any polynomial will map to roots of the same polynomial. Even if it is irreduced, if it is a irreducible polynomial, then all the roots will be there. Okay, that is one thing. The other thing, if it is not a irreducible polynomial, then it will have some factors, right? Irreducible factors. Then if the root is in the first factor, then other root will be in the same factor. That is what we need. But it will stay in the same polynomial, right? Root of the same polynomial. So roots will permute. So what is happening? So you know that xi's will map to xj only. So at max what can happen? It will have all the options, right? I will map to j for all I or j at max. uh, I don't know, at max I'm just using so this can only happen, nothing else, right? There is no other option. It's just either xi will map to xj. This is not required that it will map to xj for every j, but in some cases it might happen, in some cases it might not. But what maximum could happen? So you can actually think of automorphisms of k algebra, k x1 to xn, is isomorphic to Sn, and where n is actually what you are just permuting xi's, right? Sorry, not isomorphic, I'll just say a subgroup of. Okay, that I'll also prove. At least I'll say a subset of. You can think of this as a subset of this, right? Some permutations, because as x1 to xn, what it is doing, it is mapping every element to every other element. All the permutations are there in the symmetric group, right? So automorphisms can be realized as the permutations of these xi's, since xi's are roots of the polynomial f. So this is one thing. We know that this is a subset of S x1 to xn. Now it is given that this is actually equal to, or if you want, this is also isomorphism thing, but anyway. So this is actually given that this is same as exactly this, because since Galois group of kx1 to xn, whatever notation has been given doesn't matter, Galois group of this is given to be of the cardinality and factorial, right? That is given, that this is n factorial. Now what you need to prove? That you need to prove that uh, you cannot so basically it has been asked that you cannot take fewer than n minus 1 excis to generate this. So to show k x1 to xn is not equal to xi1 to xi, let me say I minus 2 for I1 for actually I can number it, that doesn't matter. Is that okay? So what I did, so it was asked that you cannot generate this kx1 to xn, this extension, this field extension, uh, in the you cannot generate by just n minus 2 xis or fewer than that, because fewer than n minus 1, right? It was saying fewer than n minus 1, so you say it cannot be generated by any of n minus 2 zeros, right? And then it will be suffice to say that it will not be generated by less than n minus 2, right? If it is not generated by n minus 2 zeros, then it won't be generated by any of less than that, right? Do you agree?
Yes, yes, ma'am.
Right? So that's what we need to prove. And the only condition we know that this is n factorial. The Galois group is given to be n factorial.
Factorial, huh?
Right?
Yes.
So it is simple. We just think what happens here in this extension field. So what you just do, even I can write xi1 to and so on xin minus 2, and you write xi1 up to and so on xin minus 3. Okay, so what I am doing, I am attaching one by one, okay, adding, or I'll just use dots. Okay, so what I am doing, I am taking k, or if you want I can write one more. kxi1 comma kxi2, you have kxi1, you have k. Okay, so you have this extension, tower of extensions, field extensions, right? Now in this chart, what we are doing, we are just attaching one by one exercise. Okay, we are just including that, and we are just taking smallest subfield generated by the previous field, previous subfield, previous field plus one element. Okay, is that okay what we are doing?
Okay, ma'am.
Okay, now you just tell me what will be the extension, what will be the degree of extension of this one.
Mm.
So
Mm.
these are all the roots of just
Oh, yes, yes. It is the roots of minimal polynomial x.
Mm-hmm.
Degree of the first tower k
Yeah,
to k xi is the degree of the minimal polynomial of xi. Okay.
exactly. And what will it be? It will be it must be less than or equal to n,
Yes,
because
yes.
f is given to be, you know that f of xi, f so these are the zeros, so f of xi will definitely be 0, right? Because
Yes,
these are the zeros,
yes,
right?
yes.
Now at the first step, we don't know that f is irreducible, that we don't know right now. Okay, so we cannot say that this is the minimal polynomial, but minimal polynomial of x I comma f will divide f, right? Because f is a polynomial which satisfies uh, when you evaluate at xi, that will give 0, so it will be in the kernel, right? Oh, how did I write? xi comma the base field, right? Right now this, even let me write like this, it's fine. Okay, so this is true for xi1 also. So this will be less than or equal to n. Okay, now what about this extension? One thing you have to consider now, you know that f belongs to kx, that you know, right? It is
Yes.
given that. Now now in kx I1, you can write f to be x minus xi1 into some g in kxi1, because you know that this is a root, right? xi1 is a root. So first thing, in kxi1, so always think where are we looking at it. So you know that kxi1 is kxi first, if you look f in kx, then it is something, we don't know if it is a reducible, we don't care. But now when you go to kxi1, right, in the bigger field, now you know that f has a root xi1, right?
Yes.
So you can actually divide by x minus xi1, and you know that this belongs to kxi1, and this also belongs to kxi1. So when you divide it by the division algorithm, g will also be in kxi1. So you can actually take that factor out. That is one thing you can do. This is always true, like always true mean, because we are in field, first thing. Second thing, you know that using the division algorithm, so basically what you do, when you divide it, you just take what coefficients you get, you only get coefficients, either in the divisible, either will it be like something inverse of that, which will always be there because you are in field again, right? So g will be in kxi1 also. So uh, you can actually factor out this x minus xi1 in kxi1x. Okay, is this okay? Because this step is crucial, even I'll use it in the next question also. So if you understood, we can actually do induction and get the things. Hmm.
Here x minus x I1
Hmm.
into g some polynomial,
Hmm.
and x minus x I1 belongs to this field. Okay.
Hmm.
Mm, and a belongs to this. Okay, then g must be belongs to in this by
Hmm.
division algorithm.
Yeah,
Di-
you what you are doing, that is always true, like so you do this, what will happen, you when you divide it, you just take the multiple and these things,
mhm.
right?
Okay, okay.
Right, so the coefficients will be where, coefficients will be some multiple of
Mm,
xi1, or some
yes.
multiple of f, that will be like, or maybe in the divide thing. But it will still be in the field, because we are talking about field, we are not talking about ring. So division is there,
Okay.
inverses are there, so this will always be in the field. So that's what we are using. Okay, so
Okay.
so you can so this implies minimal polynomial of, or so what you can say, degree of g will strictly less than degree of f. It could be more than that, we don't know, that there might be square and everything, these kind of things happen. Or for example, if you have one root, you have so many roots of f, so you can factor out that. Okay, but we don't care, we are just, even in this situation, we don't care about g is irreducible or not. But we know that degree of g will be strictly less than degree of f, right?
Yes.
Now now consider, now let's go to the next step. Okay, next step is this, sorry, not this. Now what about this extension? You can write it properly in the induction form. Okay, in this extension what we are doing, we are attaching this element. So even without loss of generality, you can just write it to be 1 2 3 4. I'm just writing I1 I2. I started with that, so I'm just using it. Okay, so you are adding this element now. Now this is also a root of f, and now can you say that this is also a root of g?
Yes. X1 is a root of, yes, yeah, yes, yes.
Right, because g is something which is just by dividing x minus xi1, because xi2 will be there because that is a different root, that will definitely be in g because that is a root of f.
Yes, yes,
So
ma'am.
uh, so g of xi2 and g of xi2 will be 0, right? That will be a root. This implies minimal polynomial of xi2 in k, now not in k, in k xi1, because we are now, the base field is this. Okay,
Yes, yes, ma'am.
minimal polynomial of this will
Right, G
divide
equal
g,
to 2.
right?
Right.
Okay, this will divide g. So this implies degree of mu xi2 k xi1 will be less than or equal to degree of g, which is strictly less than degree of f, that is equal to n. This implies degree of mu xi2 comma k xi1 will be strictly less than or equal to n minus 1. Can I say
Mm.
that? Because strictly less than n means less than or equal to n minus 1.
Yes.
So this extension degree turns out to be less than or equal to n minus 1. Because again this evaluation map, so you have this mod and everything. So degree of this is enough to get the degree of vector space, right? Extension. Okay.
Okay.
So what you are getting actually, so by induction, I've not properly wrote it, by induction, you can actually get, you have k, you have kxi1, you have kxi1 comma xi2 up to and so on. I'm just writing last one, I n n minus 2, and you take kxi1 kin minus 3. Okay, so just break it in pieces and you get the thing. So here you are getting less than or equal to n. I'll change the color. So this is less than or equal to n, vector space dimension. This is n minus, okay, so this is less than or equal to n, this is less than or equal to n minus 1, this is less, okay, there's
N
nothing
minus
here.
2.
Yeah, here what will you get? If you see, you can think of the base field, what base field is, and how many elements you are away to attach, so that's n. So here what will you get? In the base field you have to attach 3, right? N minus 3, n minus 2, n minus 1 and n, right? I1 to in. Is that okay?
Yes.
So I'm just using the recursion. Okay, so this implies, so by this tower of extension formula, k of xi1 up to and so on xin minus 2 over k is actually less than or equal to n into n minus 1 up to and so on just 3. Okay, 2 is
Yes.
not there, so this
Mm.
is actually equal to n factorial by 2, which is strictly less than n factorial.
Mm.
This implies this extension cannot be same as, okay, this kx1 to n minus 2 cannot be same as x1 to xn, and we are done,
Okay.
right? So
Yes.
basically what we are doing, and now in the next step what will happen, if you just think about the tower here, in the next step that will be less than or equal to 2, right? And when you get less than or equal to 2, it's just like you have n minus 1, in minus 1. So you don't need all n actually. You can get the extension actually just by n minus 1 elements,
Okay.
because when you reach at the next step, the next extension will be of 1 degree, that is exactly the same degree. So whether you write xn here or not doesn't matter. So
Okay.
you can actually get it just by n minus 1 elements at most. So again, if it is of n factorial degree, then it has to be exactly n minus 1 or more. It cannot be fewer than n minus 1. That's what we needed to prove. Okay?
Okay.
Very good. So actually it is saying that when you have n factorial thing, you have everything, like all the permutations, not less than that. And so it must be irreducible and whatnot, irreducible, no, separable polynomial. It has to be, because there is no other option. Okay, very good. Let's see this question. Let fx be an irreducible polynomial of prime degree p over the field k, over a field k. So that means f is in kx, which is irreducible of prime and irreducible, and degree of f is p, which is a prime number. Okay. Okay. So that's what we have now. Let kf be the splitting field of fx over k. So kf is given to be the splitting field of fx over k. Next, you take further let e in f kf over k, which what does this mean? This, you know, that this set we represent for the set of intermediate subfield of kf over k. Okay, so this is the collection of all the subfields, and E is one of them. Now show that, to show kf over k is less than or equal to p factorial. So that we need to prove. Oh, sorry. I wrote something from hint. But show that fx is still irreducible over E if and only if P does not divide, I can write it in, P does not divide E over K. Okay, so that's what we need to prove. Let's go through what do we have. Fx is an irreducible polynomial of prime degree P. Okay, and kf is a splitting field of fx over k. Okay, so you have this extension. So you have kf, a splitting field, and at the base you have k, and now you have some polynomial here, f in kx, and kf is the splitting field of f. Now you take any intermediate subfield of kf over k. Okay, you take any subfield. So we need to prove that fx is still irreducible over f. So whatever you so basically you are saying, for example, you have let's say q, same example, let's take it. So you have this, let's take just q. So you take q and you consider f to be what? Let's say x cube minus 2. Okay, let's say this is your f, and you take e, and I'll just attach anything, not any root of x cube minus 2. Let's say I'll just use root 3, doesn't matter, right? Then f will still be irreducible in q root 3, right? And here in the splitting field, you have all the roots, cube root of 2, and you have omega, whatever you represent. Okay, right? uh, if you see, this is also irreducible. So this belongs to qx, and this is irreducible, and f belongs to q root 3 also, and still irreducible. Okay, so it could happen that we know now. And for example, in this case itself, fx is still irreducible over e if and only if p does not divide e over k. Okay, so what do we know now? Yeah, so p does not divide e over k means p does not divide. So what is the extension degree? This is 2. Okay, and this is your e, this is your k, and this is kf. Okay, splitting field. So you can see that, and what is p? P is 3. So 3 does not divide 2. So this is good. Do you agree? This example you understood?
Yes, ma'am.
Okay. So basically we need to say that if E is still irreducible over E, then P does not divide E over K, and this is a if and only condition. Okay, great. For example, so for example, if I just attach this element, q cube root of 2, then what will happen? Okay, there is one more thing. This example is not good actually.
Why?
Because this is not an extension, right? Root 3 is not here.
Yeah. Oh, yes, yes.
And this is a splitting field, so root 3 cannot be there. So I have to modify, and actually I have one good thing to do right now. So for example, if you that's what was confusing also, but yeah, now it makes sense. So for example, if you attach this element, okay, so I'm showing two things here. Okay, f is fixed, f is x cube minus 2. Now for example, if you attach cube root of 2, then you know that f will be what? X minus cube root of 2, and this will be x square plus cube root of 2 square plus cube root of am I writing very small? Can you read it?
Yes, yes.
No? So f will split. If cube root of 2 will be there, it will split, right? You know that. Is that okay? Because one root is there now, so one root is there, so it will make it x minus cube root of 2 and whatnot. Okay,
Okay.
right? So this is a degree 3 extension, because you know that cube root of 2, that the minimal polynomial is 3, so minimal polynomial of q cube root of 2 over q is 3, so this will be a degree 3 extension. And now you can see that p divides this, so this is not so p divides this, so this is not, so you can see that p divides it and it is not irreducible. This splits, f splits in some factors, some irreducible factors. Okay, but now for example, in one situation, what you do, I'll just copy this, I just don't want to erase it. This, yeah, and I can change colors. So what you do, you just remove this, and now I'm modifying by what? You take same thing. Now what you do, you attach omega. Then what will happen? Omega is not a root of f, so it will not it will not factor out. It is not a root and this is a cubic thing, so it will not factor because one of the root has to be there, because right, because root is cube root of 2 omega and these kind of thing, but not omega is not a root, right? So this will f is irreducible in q omega. And what is the extension degree, can you tell me?
Q to Q omega.
Yeah, q omega to q, this extension.
It is 1 second. It is 3.
Why 3? What is the, so q omega over q, what will it be?
It is
Degree
minimal
of,
polynomial of the omega.
right, minimal polynomial. What is the minimal polynomial of omega?
Omega square plus omega plus 1.
Right. So what will be the degree?
Oh, sorry, 2. Yes, yes.
Yeah, that's what is required here. So the degree of extension will be 2, and now you can see that 2 does not divide, 2 does not divide 3, so it is irreducible, so everything falls nicely here. So what does this say? Fx is still irreducible over e, which is this. In our case this was e. So one case we have seen where it is reducible and p divides it, and other case we have seen that it does not split, like it is still irreducible and it does not divide it, right? Good.
Yes.
Okay, so as some example came up, so but anyway we are going to prove it. So okay, let's see. So you have ef and you have, what was it, e, oh sorry, kf. So you have kf, e and k, and very good. So let us see. So let's prove there are two sides. Let's prove one side. For example, let's say this one. Okay. Right. So you have kf over. So this implication means let e maybe p does not divide e over k. Right? We are assuming this thing. Yeah. Okay. Uh, okay, we need more tower here. Okay, p does not divide it. So what does this mean? Okay, so let you have a polynomial. Okay, so let alpha be a root of f in kf. Okay, you consider a root. Okay, kf is the splitting field, it will have all the roots, so let alpha be a root of f in kf. Then you consider k, you have e already, so what you can do, you can just attach this element. That is one option, right?
In the first diagram, it is K, E, K, and the proof in this direction.
We need to okay, yeah, to show
Okay, to so yes.
what do we know, what do we need to show? If p does not divide, then f is irreducible. F is irreducible in e also. Okay,
Okay.
it is irreducible in k, that we know that. So f will still be irreducible in e, that we need to show. Okay. Okay, so let alpha be a root of f in kf. You consider one root. Now you take different towers. So you have k, you have e, and you attach alpha, and so basically you have this tower, right? So I can make it nicer if you want. You take e alpha here. You have this extension, you have from here also. You can go from two ways, right?
Yes.
So this is a lattice of subfields. So this is a poset and it has under inclusion. Okay, it has join and meet. Very good. So okay, so what you can do, you have now let's calculate what this will be. So there are two ways to go. Either you can go from E alpha K alpha, and this is K alpha over K, and the other way is you take E alpha E, and you have E over K. Is that okay? So this one is this, and this one is this. Good. So there are two ways to find this extension. Okay, and these are all finite. That's why we can do, because kf is a finite extension. We are just taking roots of f that will be finitely many x1 to xn. So, and this will be algebraic, and so this will be a finite extension. Okay, because f is a polynomial of degree n, so you will have just n minus so every n degree polynomial. How shall I say? Yeah, so these are finite towers we have considered earlier, right? So like this also, and all the elements are algebraic, so it will be a finite extension. Okay, so you have that. Yeah. So this is E alpha. I'm just writing it side by side now. On the one hand, you have this. On the other hand, you have this. And what do you know about these things? Let us see. So, can you tell me what is this? K alpha over K. Alpha
It
is
is
a root of.
polynomial, degree of minimal polynomial of alpha in K.
So, what will it be?
Okay. Alpha be a root of f n.
Given that f is irreducible in
E.
in a base field K. So E we have to prove. In the bigger field, it will be still be irreducible. That we need to prove. But we already know that f is irreducible in K, right? So f is given to be irreducible of prime degree. That we know,
Yes.
right? So we need to prove that this is still irreducible in E. So now you know that this will be, as you said, this will be the degree of minimal polynomial of this. And since irreducible polynomial and monic polynomial will differ by just the coefficient, okay, by some scalar. So it will still be same, right? Degree of f, and that will be what? That will be p. It is given to be the degree of f is p. So this you know. Okay, and now okay, now what we also know, that this extension, so E over K, we know that does not is not divisible by, and just collecting all the information we have is not divisible by P. Okay, so let us see. We have P into E alpha. So what can you say? What can you say from here? That okay, I can write once again. One more. So you have E alpha over K, and you have E over F. What can you say about P in this case?
Yes.
What can you say? P will divide which factors?
Okay. P must be divide a one of these. Yeah.
Yeah, one of this. But you know one more thing, that E over K is not divisible by P. That's what we
No.
assumed.
Okay. Okay. The must divide E alpha.
E alpha over, or I have written something. Yeah, this is E, right? So E alpha in E alpha E. So you have this one, right? E alpha E and E over K, right? So this P will divide E alpha over E. And what will E alpha over E be? Degree of minimal
degree of
polynomial, yeah,
and of alpha in P.
in E, right? In the
E.
base field.
Yes, yes.
In the base field. And can you tell me what is the relation between this and mu alpha comma K? So K is the
Mu alpha comma K, mu alpha comma E must divide mu alpha comma K.
exactly, right? Since this implies, and this is equal to what? This is equal to P. This implies, and you know what P, oh sorry, what I am writing. So this implies degree of mu alpha E should be less than or equal to degree of mu alpha comma K, right? And we have that P divides degree of mu alpha K. So this implies, so you have two conditions. I should be writing nicely. So yeah, this is equal to degree of mu alpha E. So this is first equation and this is second equation. What can you say from first and second now? Can you say what can you say? So,
Yes, I am saying if you have the divide degree of alpha and degree of mu E is equal to P. Oh, okay, okay. P divides mu of alpha K.
divides.
Uh,
Not divide, right? It divides this. So degree will be just less. So what we can say, P divides degree of mu alpha E, which is actually less than or equal to P. So divides means this implies it will be bigger than P, first thing.
Yes.
That we at least know. This implies degree of mu alpha E will be greater than or equal to P, because it is divisible by P. And from the other hand, you know that mu alpha E should be less than or equal to P, right?
Yes. Yes.
Okay, so from these two, this implies degree of mu alpha comma E. So I should not be writing like this, maybe. So first is really, anyway. Yeah, that looks good, I think. Okay. Understood? So
Yes.
we can say that from first and this is second, we can say that degree of mu alpha E is equal to P. And what does that mean? You know that, and now you know that this implies mu, and again the same thing. Basically what you are doing, you are saying that degree doesn't decrease, okay? So mu alpha E divides mu alpha K, and degree, this implies this, and degree of mu alpha E is same as degree of mu alpha K, right? Both of these are same. So this implies these polynomials has to be the same, because these are monic. So up to scalar also, like there's no scalar we need to consider. So what you are saying, it will be some factor of, firstly mu alpha E will be some factor of mu alpha K. That is one thing we know. Now we are saying this factor itself is of degree P. So it has to be the same, because the bigger one, the polynomial mu alpha K itself has degree P. So it's and if its factor has the same degree, then it has to be the same, right? And what does this mean? Since this is irreducible, so this, firstly this has to be irreducible,
Yes.
right? Mu itself, this implies mu alpha E is irreducible in E and it stays the same. So okay, what I was saying, mm, f is still irreducible. Why did I consider mu alpha? Okay, okay, doesn't matter. I should write somewhere. F is, so I'll just write here, f is same as mu alpha k up to a scalar, right? Up to a scalar. So uh, that scalar will still be there. So if mu alpha k does not split, f will not split. So c will be there. If you just think about f. Okay, I should have used f itself. Why I did that? Do you understood? So mu alpha k, so firstly what is this? F is irreducible. Okay, so mu alpha k will be just multiple of mu alpha k will be the monic factor of f. Monic factor, what I mean by that, this is the condition where c is some constant in k, right?
Yes.
Because f is irreducible. Okay, f is irreducible. So this will complete statements can confuse. Okay, so f is irreducible, so it will be a multiple of mu alpha. Okay, that is good. Yeah. Okay, what I need to prove, so basically f is mu alpha is irreducible in E, and I should not write this enough. This implies f is irreducible in E. Okay, because minimal polynomial is same, so f is what? F is actually what? C into mu alpha E now again, and that is same as this is mu alpha k, and that is C mu alpha E. So this will still be reducible because that is still mu, so it will be reducible, right? Mu is the minimal polynomial, and minimal polynomials are irreducible. Is that okay now?
Yes.
Okay, let's prove the other side. Okay, so for other side, now assume that this is irreducible. Let f be irreducible in f be irreducible in E. Okay, and now we need to prove that to show P does not divide E over K. Okay, so we need to prove now this. Now think about it. Can you use the same process which you just did? Let us see. Can we trace back the things? Okay, so can first thing, since f is, so you again consider that alpha doesn't matter, right? Alpha, same, alpha is a root. Right, again, alpha be a root of f in, of course, ef is there, so root is there. Okay, so alpha be a root of f. Again, let's assume that. Now you have again that tower E alpha, and you have this K alpha, and you have this, right? So again you can consider E alpha over K. I'm not writing K, I'll just write equality now. From one side, from this side you will have this, and from the other side you have E alpha over K alpha, and you have K alpha over K. Okay, so these things we need to know. Let again alpha be a root of f in EF. Okay, now tell me, so you have actually did K alpha over K, I'm writing like this. So again you know that this will be what? Degree of f. Alpha is a root and f is irreducible, right? So degree irreducible. So degree of f, that is equal to p. So that we have. Can you tell me what will be the degree of this? Sorry. That will be what? Again degree of f? Because f is irreducible and alpha is the root of f. And you are talking about the same alpha. You are not changing the element. Now you will consider degree of mu alpha e, and you already know there is a irreducible polynomial which has 0 to be alpha. So this will again be degree of f, because now the assumption has changed. Now you know that f is irreducible in E. Do you agree?
Yes.
Right? We are doing the same thing. What we got at the end in the first part, we just got that degree of mu alpha E will be P and f will be the same, like the same polynomial will work. So you will have P. So you can see that this will get cancelled. Okay? Cancelled means okay. So this will be what? E over K, and you have P, and the other side you have P E alpha over K alpha. Okay, so this will be E over K, same as E alpha over K alpha. Okay, right? So you know this much only now. But now you have to prove that P does not divide this vector. But right now you don't have that anything, because you don't know about E alpha over K alpha. You don't know about that, right? So we need to do something else. Something else means we have to use this splitting field and what we did earlier. So you have EF and you have E. Okay, I'll write it nicely. Okay, there is a claim I want to use. Okay, we just studied what EF over K will be. Sorry, this is K, right? What is KF over K? Can you tell me? Can you say that this is less than or equal to P factorial?
Yes, it is the degree of the polynomial. If n degree polynomial is splitting field degree less equal to n factorial.
That you know, right?
Yes.
Okay, and you can also see that from this above thing we did, like what you are doing, you are attaching one element one by one. So
Yes, yes, yes.
degrees are like n minus one. So it's like that. But I am also claiming that kf over k will just not be less than, this will also divide p factorial, not just less than. Less than is a weaker condition than divisibility, right? Now you are saying kf over k will the vector space dimension will have exactly these factors, p minus 1, these kind of factors. So let's prove this claim, and if we do that, then we are done, in the sense that, so assume the claim. Can we do now? I'll prove the claim, don't worry. So if you assume the claim, then what will happen? You take kf. Now you have to somehow use that e over k. So we have to prove that p does not divide e over k. So we have to go to this p factorial thing, right? Something of that kind. So you take this, okay, and so I need to somehow use okay, what I want to use, yeah. So you take kf, right, okay. So you consider E alpha over K alpha, which we did earlier, and you take K alpha over K, and I might might be using so many things, but doesn't matter. So you just consider this, and this will be what? E alpha over k, right? So what I'm doing, I'm just taking E alpha, and I'm taking k alpha and k, right? So just this extension. Why I'm doing that? Because I know what is the information about this. This is exactly p, right? K alpha over k is p, and E alpha over E is p. That we know now, right?
Yes.
Okay. And now, can you also see that this will okay, I want to go to this, right? So you can also write this will be kf over E alpha. Might have writing so many things, but you can concise that. So you just take this. I actually want to go to this p factorial, so I somehow go to this k f over k. So you have you can consider this extension also. So here itself you just take kf, right? So what you are doing, you are taking from this to this, and you are writing, yeah. So let me write directly, okay? So there will be no confusion, because by the chain you can actually write it in 3 times, right? Oh, not k. Okay, is that okay, this step?
Yes.
Now you know that this divides p factorial, right? And you know that this is equal to p. So you know that this whole thing, so can you say that this whole thing kf over k e alpha over k alpha, this will divide p minus 1 factorial, because there is only one factor of p, because p is prime, right?
Yes.
Since p is prime, okay, p is prime, so if you eliminate p will get cancelled from this factor, right? P will get cancelled, then you have only p minus 1 factorial to talk about, right?
Yes.
Because p is prime, that is important, because if p is not prime, then you can get so many factors of that, right? For example, if you talk about 4 factorial, then if not 4, let me say something else. Is it not? Okay, doesn't matter. So can you say that? Anyway, so p is prime, so p will get cancelled, so you will just get p minus 1 factorial, right? So this implies, okay, for next step it is important, yeah. So this implies kf over e alpha, I'm sorry, e alpha over k alpha will divide p minus 1 factorial, and this implies, now you can say that, right, that is important. So for so you can say that p does not divide e alpha over k alpha, right? Right, because this divides p minus 1 factorial, that means it has some factors of smaller things, right?
Yes.
Yeah, right. Still want to say something. Yeah, I want to actually say that if p is not prime, then it will not work. For example, if you take 6 factorial, okay, then 2 into 3 is also there, so 6 will come here, right? So you have 4 5, 4 into 5. So if 6 will get cancelled, so actually you are not using here. So if p get cancelled, then of course this the remaining factor will divide p minus 1 factorial, and then if it divides p minus 1 factorial, then you can say that p will not divide e alpha over k alpha, because since p is prime. Here you are using the fact that this is prime. Why? Because if p is not prime, then you can get from the smaller ones that value n factorial, right? 6 you can get from the smaller ones. Even though 6 got cancelled, you are just talking about 5 factorial. So p minus 1. So if p is not a prime number, then you can still get 6 from the remaining ones, right? But if p is prime, then you cannot get, because p does not have factors other than 1 or p. Do you agree?
Yes.
Okay, so that's where we are using the fact that p is prime. Okay, so and this implies now you have already proved that e alpha over k alpha is same as e over k, right? We did that here
Yes.
from star, right?
Yes.
So we will be done. So what do we need to prove now? The claim. Because I have assumed the claim, I have used that this divides. I am not using the fact that this is less than or equal to, because less than or equal to does not guarantee about the factors, right?
Yes.
Okay, so we have to prove that this divides. So proof of claim. Okay, so claim is kf over k divides p factorial to show. Okay,